Section 3.2, the derivative as a function. We just learned how to calculate the derivative, otherwise known as the slope of the tangent line, at a particular point. But we realized that this is such a useful value to calculate that it might be interesting to find the slope of a tangent line at multiple points. If we have a nonlinear function that's changing, it makes sense that we want to ask what the slope of the tangent line is at multiple points along the function. So that's where the derivative function comes in handy. We're going to learn how to create a function that allows us to calculate the slope of the tangent line, the derivative, at any point we want without having to start from scratch. Let me show you what I mean. The derivative function looks a lot like what we did in the last section. The only difference, though, is that we're not using one specific value for x. We're going to leave x as a variable. That way the outcome's a function where we can plug in whatever x value we want. So the limit that you see on the screen should look very familiar. It might look more familiar if we had an a here, an a here, and an a here. But remember that that a value was some specific point that x was approaching. So now we're going to learn how to do this without having one specified value for x, and instead create a function that allows us to use whatever x value we want. For this section, the questions will look very similar to the last section, except the x value equal to some constant won't necessarily be the starting point. So here we're looking at the function root x, and we want to find the derivative of that function. So all we have to do is calculate this difference quotient the same way we did in the last section, but notice we're leaving the x's as x's. We're not replacing them with a's. And that's it. So we need a few things. We need f of x. We also need f of x plus h. Well, f of x is pretty simple. We're given that definition. F of x is root x. So we can just copy that over. However, f of x plus h means that I need to take that definition, root x, and replace the x with x plus h. So this would look like the square root of x plus h. And then our difference quotient, the thing that we're going to take the limit of, would look like the square root of x plus h minus the square root of x, all divided by h, and we're going to allow the limit of h to go to 0. So whatever comes out of this, once we're done simplifying, that would be our derivative function. So let's see if we can evaluate this limit. If we plug h in directly, we get indeterminate form. 0 on top, 0 on bottom, which means we need to do a little bit of algebra scratch work here. Remember that if we have an indeterminate form with radical terms that have a sum or a difference, we should use the conjugate. So what I'll do is copy over the function, the difference quotient, and then we're going to multiply that by the conjugate on top and bottom. So it's the numerator that has the radical in it, therefore it's the numerator that we will conjugate because we want to get rid of that radical. So I copy over the numerator terms, but I change the sign between them. Instead of a minus, it's now a plus. And I'll pop some parentheses around all of the numerators, all of the denominators. That way we know that we have to distribute. In the numerator, I have a difference of squares that's been factored out. Oops. So I know that I can just write this as first term squared minus second term squared. So that would look like x plus h square root squared, but we know that the square root and the square cancel off, so that would just be x plus h, and then minus the square root of x squared, but again the square root and the square cancel each other out, so our numerator looks like x plus h minus x, and while we're here, let's simplify that. If I have an x and a minus x, then really I just have an h. I'm going to leave the denominator factored, just like we have in the past examples with indeterminate form, and that's because we're really hoping that something will factor off and fix this indeterminate form that we've experienced. And in fact, I can see that the h in my numerator divides off with the h in my denominator, so that expression we started with is literally equivalent to 1 over the square root of x plus h plus the square root of x. So instead of sticking with this indeterminate form, let's rewrite our limit with our new version, our twin function. That is 1 over the square root of x plus h plus the square root of x. And now we can plug in h going to 0 without getting an indeterminate form. That results in 1 over root x plus root x, or 2 root x. Now this is what I want to point out is different from the last section. The answer to this limit is a function. I can tell it's a function because there is a variable left inside of it. It's not a simple number answer like we got in section 3.1. It's a function itself. And what's great about this is that this function will produce the slope of the tangent line at any point x that we want. Let me give you a visual to go along with that. If our original function was the square root of x, then we see the green line on the graph. And we just found the derivative, which I'm going to call g of x. It's a new function, g of x, that was equal to 1 over 2 times the square root of x. Now we see that graphed on here, but we don't really need the graph necessarily. What I want to show you is that g of x, the derivative function, is going to produce the slope of the tangent line at whatever x value we want. So I'm going to let it say g of a, and then I can allow a to be a slider. So this will provide infinitely many, well, we got to be careful with our domain. If a is the input for our function, then it cannot be smaller than 0 for a square root. And we've used slope of the tangent line to graph tangent line, so I'm going to go ahead and do that here. I know the simple form for a line would be y minus y1 is equal to m, the slope, times x minus x1. I'm going to kind of shortcut that here and write that as y equals our slope, which is g at a, times x minus our x value, which I'm using a, and then plus our y value at a, which would just be f at a. And we can see here that this line that I've just created is tangent to our curve at different points along the line. And I can even show you the point that we are tangent at. So if we follow this point A, we can see exactly where the tangent line would fall using this function. So rather than calculating the derivative 10, 20, a million different times, we can generate the derivative function and use that function to generate whatever point we want. Let's try another one. Most of these problems are going to be straightforward, where you're given a function and you're asked to find the derivative function. The hard work here is the algebra. So let's do some practice. If the function that we're looking at is x squared minus 2x, then we need to find f at x plus h. And we need to be very careful. Wherever there's an x, we are going to replace that x with x plus h. So we have x squared minus 2x, and like I said, wherever there's an x, we're going to replace that with x plus h. A very common mistake that I see here is not applying parentheses correctly. If it was x that was squared, then it's the entire x plus h that's being squared here, not just the h, not just the x. And then if it was 2 times x, then I need to multiply the entire x plus h by 2. So we can't really overdo it with parentheses here. And then we multiply this out. This first term is a perfect square binomial. So I just multiplied that out using the pattern. You can FOIL it out if you'd like. And then the second term I need to distribute. Don't forget that you are multiplying by a negative here. So negative 2 times x is negative 2x. Negative 2 times h is negative 2h. If there's anything that can be simplified here, do it now. When I say simplify, I do not mean factor. Often we think simplified and factoring are the same thing. They're not. In this case, when I mean simplify, I'm saying combine any like terms that you can. Cancel anything out if you can. I don't see any like terms here, so we cannot simplify any further. We're going to plug that directly into our difference quotient. Then I'm going to start to see that this gets a bit messy. I need to next do minus f of x in my difference quotient, where my function f of x is x squared minus 2x. So minus the entire f of x function. I'm going to add more parentheses here because I need to subtract both terms in my function. If I forgot the parentheses, then this sign is going to be incorrect. But if I keep the parentheses here, like I started with, I'll make sure to distribute that negative. And then lastly, for my difference quotient, I know that I need to have an h in the denominator. And now we're ready to simplify. If I distribute this negative, then instead of having minus parentheses, I can write this as minus x squared plus 2x. And then I can see that I have a positive x squared and a minus x squared. Those guys cancel off. And I have a minus 2x and a positive 2x. Those guys cancel off. So then I'm left with 2xh plus h squared minus 2h all over h. If I try to do direct substitution here, I will get indeterminate form, but we know how to deal with that. This is a rational expression with a polynomial on top, polynomial on bottom. So our tip here is factor it completely and divide off any common factors. If I factor my numerator, I have 3 terms, and that means there's not much factoring that can go on, but I do see they all have a common factor of h. So let's factor off the h. And then in my denominator, I also have a factor of h, which means I can divide off those common factors. Now it's really important that you don't start crossing things off until you've factored. If we go back to the expression we started with, I often see stuff like this, and then the h squared minus 2h is left behind, but you can't factor just 2 terms. If your numerator has addition and subtraction in it, you have to factor that first. Over here in my scratch work, I can divide off this h because that's a product, and we're dividing off common factors. So now I come back and I rewrite my limit with the 2x plus h minus 2, technically over 1, but we don't need to write over 1. We can leave it like that. And then if we plug in h goes to 0, then we're left with 2x plus 0 minus 2. We're replacing h with 0, not x. Be careful here that you're plugging the 0 into the h. You're not plugging the 0 into the x. And that leaves us with the function 2x minus 2. So for this problem, the derivative function looks like 2x minus 2. I'm going to show you some more things in GeoGebra. So the problem we just worked on, x squared minus 2x, GeoGebra will calculate the entire derivative function. All you have to type in is an apostrophe. So if I named my function f of x, then typing in f apostrophe parentheses x, GeoGebra will automatically calculate that function for you. And it will graph it. So be careful because this can be misleading when we're first learning about derivative functions and tangent lines. Looking at this orange line, I can tell this is not a tangent line. 1, it crosses through our function multiple times. 2, it's not lying up against our function, it's just cutting through it. What that line actually represents is the slope for the actual tangent line at any point x we want. So here is a tangent line, and I've graphed this tangent line at the point, oh, I don't have that point on here, let me add that in. So a, f at a. So I picked an a value of 0.166. I can see that on my function right here in green, the point B. And if I let a change, I can watch that point move along my function. And I can track the tangent line at that point. Notice how this blue curve is just pushed up against our original function. It's not cutting through it. That looks very different from the orange curve, which represents the derivative function. So the blue and the orange lines are not the same thing, but they are super related. So what I'm going to show you is a point A on the tangent line, and I'm going to show you the slope of our tangent line. And I'm going to slow this down quite a bit so you can see the y values are changing in the same way. Let's move this up. Come on. Having some technical difficulties here. There we go. We can see the slope of the tangent line in blue down here matches the y value of the point on the derivative function. And I can pause it at any point and I can see that they match 1.6488, 1.6488. So what's happening is I'm calculating the tangent line for a bunch of different points on my function. Each of those tangent lines is graphed in blue. So as I'm changing that point, the tangent line is changing. The slope of that blue line is collected and plotted as a point on this orange curve. So as I move this slider, I can see that the y values of the orange point and the blue point match up perfectly. So I've slowed down the slider so that we can see a few particular slopes of our tangent line at a few particular points. So I can see that when my tangent line is going down, that I have a negative slope. that down here at the vertex of my parabola, I had a slope of 0. And then when the blue line looks like a positive line, then I have a positive slope. So being able to sort out when your derivative is negative, when your derivative is 0, and when your derivative is positive will help us when it comes time to graph the derivative. With the slider continuing, I've turned on the point A, which is mapping out just a few of the points that would live along our derivative function. Remember that the point A is using the x value that corresponds to the point on our function f that we're calculating the tangent line at. And the y value of that orange point comes from the actual slope of the tangent line, what we're calling the value of the derivative. And as I watch that yellow line, or the yellow point, I can see that it's starting to map out the actual derivative function. So with this in mind, we're going to try to graph the derivative function when all we have to look at is the original function itself. If all we knew were the actual function graph, we could look at it and start to determine what the derivative graph would have to look like. One thing that we noticed was down here at the lowest point, the tangent line switched from being a negative slope to a positive slope. And for a tangent line to switch signs like that, it had to have passed through 0. So we had to have had a tangent line that was perfectly horizontal. We'll dig into this a little deeper in later sections, but for now, I want to point out that when you have a valley like this, or a low point on your graph, you will have a horizontal tangent line. At that point, your derivative has to be equal to 0. So I'm going to trace up to the x value. The x value is at 1, which means f prime at 1 has to equal 0 for my function. Maybe my function is not equal to 0 all the time. Maybe it's just equal to 0 at this single point. Also, I want to point out that to the left of this horizontal tangent line, we said that we had tangent lines that looked like they had a negative slope, which means when I go to graph that, to the left of this 0 point, I know that my points all need to be below the x-axis. The slope of my tangent line should be negative. So anything to the left of that dashed line should be below the x-axis. We noticed that on the right side of that vertex that our tangent lines had positive slopes, which means to the right side everything should be greater than 0. So anything to the right of this should be above the x-axis, which is where we can color in a few points up here, color in a few points to the left of that dotted line, and we start to generate the line that we saw in GeoGebra. Let's go through that one more time quickly. I can see at this valley that I will have a horizontal tangent line at the value x equals 1. So I know my derivative has to pass through the x-axis at that x value. To the left of 1, my slope was negative. The tangent line had a negative slope, so my derivative function will be below the x-axis. To the right of x equals 1, I had a slope of a tangent line that was positive, so my derivative is positive. the values on that line should be above the x-axis. Now another way to graph the derivative is to literally calculate it and then plot that line. We can see that this is a line 2x minus 2. And if we wanted to find the x-intercept, all we need to do is set the function equal to 0. We can find that it intercepts the x-axis at x equals 1. That if I plug in points that are larger than 1, like the point 2, my output would be 2 times 2 minus 2, which is 2. So at 2, I should be at, well, my line's not very accurate, but I should be up here. So my slope should have been steeper. If I plug in negative values, I get out negative values. So at negative 2, I would be way down here. So we could generate a few points, find the x-intercepts, and graph our function that way. But if you are in a situation where you don't have the equation of the function, then you definitely can't do that. Like this one. We're looking at a sketch of a function, and we want to try to graph the curve for the derivative, but we don't have the equation, so we can't just find the x-intercepts and plot the points. Instead, what we're going to do is look for the points on the blue graph that would have a horizontal tangent line. So I see a little valley right here. This would be a horizontal tangent line spot for sure. And I see a hilltop right here, so horizontal tangent line for sure here as well. If I follow those x values down, I know that my derivative function will cross over the x-axis at those same x values. So at x equals negative 2, I have a horizontal tangent line, which means at x equals negative 2, my derivative is equal to 0. Also, at x equals positive 3, I have a horizontal tangent line, which means my derivative must pass through this point as well. F prime at 3 has to be 0. Now that I have my two intercepts down, I can start to talk about where the rest of the points go. I'm going to kind of divide this up into 3 sections. When I am to the left of negative 2, values that are less than negative 2, the slope of my tangent line is negative. So my points are negative over here. When I am between negative 2 and positive 3, then the slope of these tangent lines looks positive. And then when I'm on the right side of x equals 3, I can see that the slope of my tangent line becomes negative again. These signs, negative, positive, negative, they're going to tell me to either be above or below the x-axis. So I know I'm going to pass through the purple points. But to the left of negative 2, I have a negative derivative, so I need to be below the x-axis over here. Now I have no idea what it looks like, if it's a straight line, if it's a squiggly line. I just know that those points have to be below the x-axis. Between negative 2 and positive 3, I have a positive derivative, so I know these points have to be above the x-axis. Again, I don't really know what the shape of this graph is, but I can tell you it couldn't be a line because I have to pass through this other point. So the only way for this to work would be if I curved and came right back down to pass through this other point. So my derivative has to pass through those 2 points. And then on the other side of 3, we had a negative derivative, so we are below the x-axis here as well. So this curve that we just sketched out is the derivative function, f of x. Let's do that one more time really quick. I know I have a horizontal tangent line at this valley, so I copy that as a point on the x-axis. I know I have a horizontal tangent line at this hill, so I follow that straight down and copy that onto my x-axis. I can see that to the left of this first x-intercept that I have a negative tangent line because my slope is decreasing. Between my two intercepts, I can see that I have a positive tangent line because my slope is increasing. And then to the right of positive 3, I can see another decreasing slope, so I have a negative. So I know I'm below the tangent or below the x-axis here, above here, and below here. Now I have a lot of freedom to sketch the function, the derivative function, but I have to pass through these points and I have to follow the rules that come from the signs that I've identified. So I could go below here and then pass through this point, come above here, pass through this point, and then below here. Now, we're being a little free here with making squiggles, but at this point, all we're following are the x-intercepts and whether or not we're above or below the x-axis.